Good morning, good afternoon, everyone. Welcome to this LoRa Alliance webinar on multicast device-to-device communication over LoRaWAN, which is the complete name of our tier number 12. I am Olivier Seller from Semtech, Vice Chair of the Technical Committee of the LoRa Alliance, and I will be introducing this webinar today. So before we start, here are our regular housekeeping notes for webinars, so please read them carefully, even if you're a frequent viewer or listener to our webinars. So this webcast is being through your computer. There's no dial-in number. If you cannot hear the audio playing, please check your speakers or headsets that are connected to your computer. If you have any issues, usually pressing F5 on the keyboard will solve them. You can find additional answers in the web page that you are currently viewing. So more importantly, please submit your questions through the Q&A box on the screen. As you have the questions, you will the speaker will be seeing your questions and will be answering the questions at the end of the webcast. You don't need to wait for the end to ask the questions. Please ask them as you have the questions. So the slides can be downloaded, and an on-demand version will be available approximately in 1 day after this webinar. So I'm now going to present the speaker, Dave Kendall, who's the CTO, CEO of CNET, and who's been and is still one of the most important contributor to the LoRa Alliance, both on the technical and say strategy levels. As a consequence, he received the Lifetime Achievement Award in 2020, so that was already 3 years ago, but is still a strong contributor either on the board or in committees. So, and I really want to thank him for all the work he's been doing, and he's been also the primary author of the device-to-device technical recommendation that is going to develop today. So now I hang on to him, Dave. Hello, welcome.
Thank you very much, Olivier, for that kind introduction. Yes, as Olivier says, I've worked extensively on this device-to-device communication, but also very much hand-in-hand with my colleagues at Semtech as well, including Olivier here, as well as Davide Orfama, as well as an extended group of engineers on both sides of those companies. And then as that expanded, we'll talk about how we brought in additional companies to work with that for the implementation as well. CNET is the company that I work for. So CNET produces a core network platform, an LNS in the LoRaWAN speak. We also operate a public network here in the United States where we're based, but provide services to companies all around the world. With that, I'd like to start with an introduction, a background really about the device-to-device communication, and something that I think is really important to highlight, which is everything that we're going to talk about here are really very small incremental implementations that sit on top of existing LoRaWAN specifications. And that really, it's really, I think it was eye-opening to many of us as we looked at this, that you were able to build something that was quite different from what we originally thought that LoRaWAN would be used for, but using all of those same specifications. And there's a couple of really important benefits that come with that design methodology, if you will. And one of them is that we get to leverage all of the security, centralized provisioning paradigms associated with LoRaWAN that make it so strong in the market as well, while then opening up the capabilities to address a part of the market that LoRaWAN really hadn't been addressing previous to that. So a couple of things just to set the stage. So we have in the networking space, we often talk about 3 different critical kinds of networks. We talk about local area networks, wide area networks, and personal area networks. Local and wide area networks sometimes can be combined into one case. In many cases, these are the sorts of things that you think about when you think about Wi-Fi networks or cellular networks. And in fact, LoRaWAN is absolutely one of those kinds of networks, whether that's deployed in a building, in a campus, in a region or around the country, around the world. It's a centralized networking model. Messages are brokered through the network elements, so devices that connect to the network don't communicate directly with each other. They communicate through a network medium, and that's the same way that it is for Wi-Fi or for cellular networks as well. And in the LoRaWAN case, we have an end device, the sensor, if you will, that communicates through a gateway. The gateway is connected to a network server. The network server is connected to an application server, and ultimately the actual application itself. And then if the application wants to send a message back to that device or another device, it reverses that process, communicating to the network server to the gateway to the end device. And security is centralized in LoRaWAN space in the join server, the application server, and the network server. Personal area networks are typically very, very different. In this case, you're usually thinking about devices that are directly communicating with one another. And the security is typically decentralized, meaning that it's done physically and locally on the devices. Think about how you do Bluetooth pairing. You put your headphones in Bluetooth pairing mode, you look on your phone, you say, yep, that's the thing I want to pair with, and they exchange credentials at that point in order to form the security association between those two devices. There are other kinds of network technologies that are similar and not personal area network, but are point-to-point networks typically. So those are the fundamental concepts. When we talk about device-to-device communication, and in this particular case, when we're talking about a multicast device-to-device communication model, we're talking about combining those capabilities together. So we want to facilitate the ability for the devices to communicate directly with one another, but we still want to maintain the value and the benefits associated with the centrally administered security associations that's defined by the LoRaWAN architecture. This is super important for large-scale deployability as well as centrally controlled deployment models. And we'll get to when we talk about some of the use cases, you'll see why that's so important. In the LoRa Alliance, we have defined two such mechanisms to date. The first one to be published was the end device relay specification, technical specification 11. This defines a mode of operation, again, centrally managed, where the network server configures a device called a relay to be able to proxy messages on behalf of an end device, the device to be relayed. This particular specification uses a technique that we call wake on radio, which means that the relay is listening for a certain radio signal that causes it to wake up and then negotiate a communication with the end device to be relayed. As we're going to talk about in the multicast case, in this case as well, the security mechanisms are still centrally controlled by the join server and the network server in order to facilitate this communication. With multicast communication, the technical recommendation 12, we are doing something different. So this technical recommendation, as a recommendation, provides an example techniques, and a discussion of how to solve these problems using LoRaWAN, but it's not a complete protocol specification. There's not a certification test that goes along with this. I will say, though, and as we get to the end, what we've described here has been implemented and is in production devices out in the wild as well. One of the big differences between relay and TR12 is the desire to use multicast as a technique here. And so that means we're not using a wake on radio technique. Instead, we're using a time coordination between the devices so that the devices know when other devices they want to talk to will be listening without having to use the wake on radio technique. So a couple of the use cases that we had in mind when we were working to solve this problem. So obviously, communication between groups of devices. So we have multicast capabilities built into the LoRaWAN specification, but end devices don't have a way of addressing groups of devices. That was all done from the network side. So we want to have devices be able to address groups of devices. You can, of course, still do one-to-one device communication. That's a subset of this. We want to make sure that this communication model is survivable. That means that if the centralized network the NS and the AS and the JS were for some reason to lose contact with the group, that the group could continue to operate for a relatively long period of time without the network being involved in that. Scalability was another key consideration for us. One of the key use cases was in the gas utility space. And so you can imagine in large urban environments, there are millions of connected devices potentially that want to participate in these sorts of communication models. So we want to make sure that we have the techniques, which we have in unicast LoRaWAN and centralized LoRaWAN, things like the ability to change data rates and duty cycles and frequency of transmission, all of those sorts of things, so that we can make sure that we have a scalable deployment. And of course, in some cases, there's a desire to reduce the overall latency in communication between sensing an event and acting on an event. Where of course, we're still limited by the physics of the LoRa modulation and how long it takes to put a message on air, how big those messages can be, but we can reduce the overall round trip latency going through the gateway, the network server, the application server, and then all the way back down again by using a technique like we were going to be describing here. So a couple of examples that we had in mind. So I've talked kind of about the sensor and actuator. So the gas safety application. So you have a methane leak detector and a gas main shutoff valve as a set. In this case, in most cases, we're looking at several detectors, maybe mini detectors, and a small number or maybe one shutoff valve that controls that. You can think about this in a multi-dwelling unit in a building, for example. There's probably one shutoff valve for the entire building, but you might have leak detectors in every single one of the apartments that are there. You could look at something like motion detectors and light controllers. Again, mini motion detectors, a smaller number of light controllers is typically going to be the communication pattern there. Also, resilient autonomous operations. So another kind of key requirement is that in the event of a large-scale natural disaster that might have catastrophic impacts on the power infrastructure, on the network infrastructure. We've seen these sorts of events happen around the world over and over again. We want to make sure, we need to have the ability for the system to continue to work in the presence of that sort of an outage. And you can think about some examples here where that's obviously true. If you need to have, if you're going to use a solution like this to gain access to a building, you still need to be able to do that even in the event of a power outage. Parking systems might be another one. Panic buttons for worker safety would clearly be another one of those kinds of applications that you need that resiliency in order to have a viable solution. So with that background, we'll move over to some discussion around the implementation components on how we deliver against what those requirements are, and ultimately take a look at some examples of what we've actually done. So we'll start with the supporting specifications. So these are specifications that are published, largely unchanged. So I'll talk about one small change here in a minute. So we have the LoRaWAN Layer 2 specifications. This really works with any of the published specifications, and we'll continue to work with specifications going forward. But clearly TSO1, the Layer 2 specification, some key elements. We're looking at multicast Class B is primarily one of the key elements there. We also support Class C for this solution as well. A couple of small, and these are not changes to the specification, but these are the way that you implement against the specification that occur here. So in the case of doing a multicast device-to-device group, we're going to specify that the frame counter needs to increase monotonically. That means continue to increase as seconds from GPS epoch. We do this because we need to have the same frame counter for all the devices in the group so that there's not a collision, so that we understand what's happening going forward. There is a consequence associated with that, which is that you cannot use the frame count as an indication of missed messages that were sent but not delivered just for this multicast device-to-device case. We also did require one small change to this specification. This errata was published back in May for both LoRaWAN 1.04 as well as for 1.1. And that change was the removal of one sentence, or part of one sentence, that forbid end devices from sending downlink frames. So downlink frames are really frames that are received by end devices. So if we're going to have a group of devices sending messages to one another, those devices need to be able to send frames that the other ones can receive, and those are called downlink frames. So we have an errata that removed that one portion of the sentence that's been published. We also heavily leverage the remote multicast setup specification, TSO5. This is part of the FOTA, the firmware update over the air group of documents, and it defines an application level multicast group management protocol. So this is how, when we do firmware updates, we build a multicast group. You can use this part of the specification without doing any of the firmware update, just to manage multicast groups. So in the Ethernet world, this would be called GMRP. In the IP world, this would be called IGMP. It's an IP multicast group setup protocol. Very, very similar concepts, but we're going to leverage this as is from that part of the specification. And how do we do this? So this diagram here will start to show how this happens. So the first two steps here are part of the standard multicast group setup request. So the application, through the application server, sends commands to the end devices on the left-hand side that it should trigger a multicast group setup request. That will tell the end device, here are the parameters. I want you to join a multicast group. Here are the parameters for that group. The end device responds back with an answer confirming that it is in fact now part of that group. At this point, the application through the network server can send commands to all of the devices in that multicast group with a single transmission per gateway. So that goes to all of the devices that are part of that group. We will need some additional information though, and that additional information is in the second step here, which is going to be down at the bottom, which is going to be how we set up the ability for that device to be self-coordinated as well. Move over to that. So this first command, this application layer group member setup request, is going to do a few things that the TSO5 doesn't do. And it's going to, first and foremost, give the end device its formal group number and its membership number within that group. So we call that the multicast group ID and the membership number. So in traditional multicast, the end device really doesn't need to know that kind of information because it's just on the receiving end of the messages. But now when we have devices that are communicating one to the other, we need to be able to identify the group that the device is part of, and we also need to be able to identify the membership number. So which member of the group is it? And you'll see why we use that in the future, but clearly one of the most important things is this gives us the ability for a message sent to that group to be identified with a small number, these 2 bytes, that identify the sender of that. In LoRaWAN, we don't have a sender address in the base protocol format. It's only the destination address. So this gives us a sender identifier. The next set of fields in this group membership setup request define transmission control. So when you have many devices that are potentially part of a group, and we have this scaled to support hundreds or thousands of devices, that might be an exception case, but we have many devices that are trying to communicate with one another, and you have the possibility that you have different groups that are near each other. You're going to want to be able to control those groups in a way that give you a high probability of actually getting the messages sent that are important to be sent and received by the end devices. So we're doing a few things in this case. One of them is this transmit opportunity field. This transmit opportunity field, really imagine again back to class B. So in class B, we have slots. We call them ping slots in the past. Those ping slots are your opportunities to receive messages in a class B capability. So our transmit opportunity here takes those slots and it says how many, every N of those slots you get a chance to transmit. You can't transmit everyone. You can if you want to, but we're going to make it so you only transmit on every 4th opportunity, for example. And then in addition to that, we can tell the device in the transmit opportunity offset field where to start in those slots. So at that point, we can interleave the possible transmissions from the end devices that are part of the group so they don't step on each other. This is a slotted approach, a fully slotted approach at that point. And that would work in a group that is limited in a LoRaWAN case with Class B to around 128 total devices if they were all had, if the ping slot was basically every second. However, that may not be appropriate, and it may still require too much power consumption for listening that often, so we may want to have less opportunities, in which case we are not fully slotted. In one case, we have this transmit probability field over in byte 5. That transmit probability field kind of tells the end device that it should only transmit every so often on that opportunity that's been defined for it. And this way, again, it's a way to help mitigate the collisions that might occur with devices all trying to transmit at the same time. The final thing that we have here is also a transmit power variability, so we can enforce a minimum and maximum transmit power on the end devices that are participating, again, in an attempt to minimize the overhearing that might possibly go on. So you can combine all of these techniques together, again, in order to maximize the probability of getting the important messages through. If we think about our case with the methane leak detectors and the gas shutoff valve, it's super important that we get at least one of those "I have a leak" messages to the gas shutoff valve, so that it can take appropriate action at that point. And that's what we're using these fields to do. The next component is survivability. So we have now the ability for these devices to talk directly to each other with the previous configuration. That means that we can jump past, we can bypass that round trip latency of going up all the way to the application server and back, so we can decrease the overall time it takes for us to get a command back to that valve, for example. Survivability was the other design goal. So how do we let this group survive in the event that the network goes down? So in a Class B scenario, the network is providing a timing control in most cases using the Class B beacon. Well, if the network goes down, if the gateways are down and they're not providing beacons, how does this little group of devices still remain able to connect and contact each other? So in this case, what we have is the ability to have the group elect a timing control member. So this is a combination of things. So we look at this and we say that when the devices will send a device in the group, if you want survivability, it will send a timing control message. That message will look like, in our case, we've defined that message to look like the device time answer MAC command. So it will send that message. And in that message, it will also be conveying its member ID and the timing control field. And so we use those capabilities there to elect who the root of the timing information is. In most cases, there is a natural device or a small set of natural devices that it makes most sense to be in control of that timing. Back to our gas safety example, it's the valve. There's one valve, there's many of these methane leak detectors. The important action happens at the valve. So the valve should be controlling the timing. And we do that by setting the member ID to the lowest values. The lowest value member ID is the one that will be sending the messages. And then the timing control it controls how often we send those timing messages. The next component is generally considered optional. Obviously, nothing is specified as required here, but is really kind of optional. And this is the ability for the group to be able to understand the reachability of the other group members, which it might use to influence what transmit power it's operating at, or to report back to the network that maybe the RF parameters that were used to establish the group, things like the data rate or the frequency that it's operating on, were maybe not appropriate. So this message may be sent by all the end devices in the group, either on a unicast channel back up to the network server and the application server, and or on the multicast channel between the devices themselves. So in both cases, you're providing the receivers the ability to know what this one device's view of the group is. So if you think that you have 5 group members of the group, and this group member is saying, I only see 3, you can coordinate that, you can understand that now between the groups and use that information either in a centralized fashion, going back to the application server, or in a coordinated fashion between the group itself to then make adjustments to the RF parameters and gain that full connectivity between the group. This is really part of the examples that when we started to implement, we saw some really interesting challenges where you have maybe most of the group, 99% of the group is in really good RF contact with each other, but you've got one outlier device that really isn't. How do you recognize that scenario? And this is how we identify and recognize that scenario. So this configuration, this is a configuration of that. I'll show you what the messages, the report itself looks like. The configuration tells the end device how often it should be transmitting this report and what link margin it should be using in order to qualify the received messages from the other group members as a good reception, as good enough reception. The membership report itself contains the member ID, so who's sending it. It contains the interval over which the report was gathered. So you're going to be listening for these devices over a fairly long period. In most cases, these devices aren't always going to be sending messages to each other on a rapid basis. So maybe when I use an hour or 2, something like that, to gather the information from all of the devices. And then we have a flexible way, I won't go into the details here, of addressing a very, very large number up to the full 1024 possible members of the group in a LoRaWAN sized message. So you might need to send multiple reports in order to get everything up there, but we can fully address the entire group width of up to 1K devices using this technique. So that is the summary, really, of what is in the technical recommendation for how to implement this multicast device-to-device capabilities. I will say that as we've gone through this process, we've identified some areas for improvement that we would like to action in the core specifications themselves. These areas are fairly small changes to the different specifications, but at the end of the day, they end up giving us a lot more power. So there's a couple of things that are coming out here. So for TS05, that remote multicast group setup protocol, part of the firmware update documents, today the group lifetime for Class B has a hard limit of 48 days. And for Class C, it's a hard limit of 9 hours. 48 days is a pretty reasonable time. 9 hours is pretty small. We would like to see those expanded significantly. It's really just defining some additional RFU bits that are in the RFU state today in that specification to give us that additional flexibility. This was very much targeted at a firmware update process, and in a firmware update process, those are very reasonable limits. But when we want to have that long-term survivability, we have seen requirements from the market that even 48 days may not be long enough. And if you think about some of the natural disasters here in the Americas, for example, we had some in Puerto Rico a few years ago that lasted well beyond 48 days without power to many areas and without network access in many areas. So that's certainly something that we'd like to see improve. That will give us additional flexibility. We expect to see new Class B session parameters coming up in the next version of the Layer 2 specification, so obviously we'll need support for those as well. The other item which is being discussed in the next version of the Layer 2 spec is an improvement to decrease the dead time in the Class B beacon period. So the Class B beacon period, 128 seconds. There's 128 ping slots, but there is a section of time at the beginning of that where no messages are allowed to be sent on the group. And that's due to this beacon dead time period. We can adjust that, and we've recommended a way to do that by a very small change to the ping slot width. So today they're defined as 30 milliseconds. If we define those as 31 milliseconds, we can reduce that dead time to less than a second. And that's important because that gets, again, back to our latency requirement. So that dead time period, I think today is 4 or 5 seconds. That's a fairly long period of time where I can't transmit right now. So reducing that certainly helps us improve that overall latency in the documentation, in the implementation itself. I want to spend a few minutes here just to wrap up as well. So that was a relatively rapid overview of the technical recommendation. The recommendation itself is relatively short. I strongly encourage all of our listeners here to download that and review that. It's very much worth the effort, I think, if for no other reason than it really shows a very, very interesting and I think innovative way that with a little bit of extra work on top of the existing base specifications, you are able to innovate in some really, really novel ways. And that's really what I think is the most important takeaway from this. Even if you're not interested in actually doing device-to-device communication, you can take techniques like this, lay them on top of these existing specifications, and start to develop some very, very interesting and powerful tools and techniques. I definitely expect that we will see something similar to what we've done here, laid on top of the relay specification to formalize a end-device-to-end device using wake-on radio capability. The fundamentals associated with both the layer 2 specification and the relay specification to build on that and deliver a similar set of capabilities on top of those tools. I mentioned earlier that the motivating use case here was gas safety, utility gas safety techniques. And I want to call out a few companies that collaborated very, very strongly with Senate and of course Semtech as the kind of the two motivating factors at the beginning. In addition to those, and I'll just list the ones that have publicly released this information at this point, but we worked extensively with LoRa Alliance members Oxit on the implementation of this on the radio module. Worked very extensively as well with two end device manufacturers, a company called New Cosmos in the methane leak detector side, a company called Lorax on the valve shutoff side. And we've successfully demonstrated this. All of those companies have successfully demonstrated this in pilots and proof of concepts with natural gas utilities here in the United States. So very, very exciting capability, and we're very, very happy to have this opportunity to talk with all of you about those capabilities. And again, strongly encourage you to take a look at those specifications and look forward to your questions at the end. With that, Olivier, I think back to you.
Thanks a lot, Dave. Once again, you can download this presentation, and at the end of the presentation, you will find these references. So as Dave said, you are encouraged to download that and read that for yourself. So we're going to come to the Q&A in a few moments, but before that, I have a few announcements to make. First of all, thanks again for attending this webinar, and please, if you're not a member already, please consider joining the LoRa Alliance. So there are numerous reasons to join, both on the marketing, leveraging the marketing of the Alliance, accelerate your time to market, boost your brand, know better the verticals, meet business partners, but also on the technical level, where you can collaborate with other companies to produce the specification. You can have access to a free pre-certification testing tool, which will be able to verify that your device is ready to be certified, to meet all the protocol tests. There is a strong regulatory support in the LoRa Alliance. So we operate, of course, in unlicensed spectrum, but unlicensed doesn't mean unregulated. There is a huge amount of regulations which we know very well, which we follow, and we also have a relationship with the regulators. So that's pretty important for the business in any place in the world, literally. So please consider joining the Alliance if you're not a member yet. The latest addition that we made to the LoRa Alliance is this LoRaWAN accredited professional program. So it's a program to give you a recognition, a technical recognition to typically boost your resume, that you could put that on LinkedIn. It's going to help you. It's going to make you more employable. There's the first a test, a sample test that you can go for. You will see from there what you need to train on, what kind of webinars or FAQs or technical spec or technical recommendation you need to read to improve and eventually pass the test. So please go here, accreditedprofessional LoRaAlliance.org. And the last announcement is our next LoRaWAN Live event, which will be held in October 11 and 12 in Tokyo, Japan. So this is a 2-day public event. Anyone can join, and you will find there keynotes, panels, live demonstration, a poster session, and an innovation marketplace. So it's really the place to be to update and do business in the Asia Pacific region. So now we can go to the questions and answers. So let's start with one of the questions from Dana. Dana, thank you for asking so many questions. So this is a question on the radio. Let me read that quickly. Given that the transmit and receive path are different, particularly those with PAs, and the downlink frequency is different than the uplink frequencies, specifically in US 915, is there an experience on efficiency of transmitting on this downlink frequency than I understand on the end device side? So I don't think we have a problem here at all, because the end device are half duplex. They don't transmit and receive at the same time. Therefore, it's not a big deal to transmit in the frequency which is usually used for received only. And by the way, in Europe or in other regions, we typically use the same frequencies for uplink and downlink. So we have this experience. Then there is a general question I would like Dave to answer, because it's been spread among a few questions, which is the difference between the relay specification and applications and the device-to-device that you've been presenting today, Dave.
Sure, thank you, Olivier, and thank you everyone for your questions. So certainly relay and device-to-device communication have some similarities in that you have devices that we would typically characterize as end devices communicating with each other. In the case of the device-to-device multicast case we talked about today, it's really simple end devices, LoRaWAN end devices that are communicating directly with each other. In the case of relay, we have a new device type, which is the relay itself, that has two modes of operation. So one is it's a traditional LoRaWAN device communicating with the network over the class A or B or C channels that it may have opened with the network. It also has another personality, which is its relay capability, which is talking now to another LoRaWAN end device that has some enhanced capabilities. So in that case, you're really building a bridge effectively from a remote end device through an intermediary end device, the relay, back into the network. In the multicast device scenario that we've been talking about here, the devices are not relaying each other back into the network. They're really forming a distinct communication mode with each other. There was another question that had to do about combining multiple multicast groups. This is possible, though it's not something that we've described in detail in the recommendation, where you have a nexus device, if you will, that sits between the two groups and is a member of both groups and could bridge messages from one to the other if that was something that was important to the application. I want to state, though, that one of the benefits, but also a constraint of what we've described here, is that it's centrally controlled. So it's not a self-organizing network. It's controlled by the network server and the application servers that are building the groups. And in that sense, the groups are relatively static. So it's not something that will self-organize out kind of node on node on node as you go out to the future. That's a constraint, but it also gives you the benefit of that centralized organization.
Okay, thank you, Dave. I think there are a few questions which on experience with this device-to-device protocol.
Yeah, so and I'll start that by also answering a few of the questions I see around support in the market for this capability. So as far as I'm aware today on the LNS side, Senet is the only LNS provider that is currently supporting this. On the end device side, there are several folks I mentioned at the end of the presentation who have end devices that do support this. So we've worked extensively with a company called LoRaWAN that makes a gas valve controller, and Cosmos that makes a residential methane leak detector, Semtech as well, and a company that is an engineering services firm called Oxit that has built a radio module that they have that supports this capability as well. And if you saw a similar presentation that I did live in San Francisco last year, we had a video from Oxit demonstrating some of those capabilities. So that's that really is the example of what we've been doing, and we've been using that group of companies in the real world doing demonstrations, proof of concepts, and pilot deployments specifically in the gas safety space. And again, that's specifically been here in the United States that we've been doing that, working with these companies to instrument and build out solutions that enable the automatic shutoff of gas valves and the detection in the presence of a methane leak detection event.
Okay, thank you, Dave. I'm trying not to get lost with so many questions. Thank you again for answering the questions. So maybe there's one question on kind of survivability. For instance, question 12.
Yes.
What acts as the multicast relay when the network goes down?
Right. So I did mention this briefly. I didn't have a diagram of the message that's actually used to enable the survivability mode. So survivability is this capability of the group to survive its messaging coordination even in the absence of the network, and in the absence of the network for potentially fairly long periods of time. Today, those are limited by those multicast group setup spec protocol limits we described before, but it can be 40 plus days in the real world. And this happens because a device, based upon that timing control information, many devices potentially in the group will begin to send, and they can do this either all the time or they can do this when they detect a loss of the network, for example, a loss of the beacon on the network. They begin to transmit a timing frame, and the timing frame looks like a device time answer. It's prefixed, and this is described in the technical recommendation. It's prefixed with the member ID field, so that contains the group number and the member number of that. The devices send that with the transmit controls that have been in place, so they're not, in general, stepping all over each other. And the entity with the lowest member ID is the entity that becomes the timing control. So if you hear a timing control message from a member that's got a lower ID than you do, you stop sending yours, and that's how we kind of consolidate down to a single time source within the group. If that member goes away, then another member, maybe all of them, will start sending the messages again. And again, go through that process of getting back down to the lowest remaining member ID as the one that's sourcing the control message. In many of the groups that we see being formed, there is a logical source of control. for example, in that gas safety one, it's the valve. So the valve is the most important element there. So we need to detect the leaks, but if we can't shut off the gas main, we haven't done everything that we need to do. So that's one of the keys that we use to prioritize the group membership numbers within the group, so that the most important devices, maybe the devices with the highest battery capacity, the largest devices, those would be the ones that we determine to be the controlling member of the timing source.
Okay, thanks, Dave. So maybe this is kind of a follow-up question. Number 28. Can a group be provisioned under a normal network, then shut down and shipped to an emergency site, and where it will operate temporarily altogether without any network? So is this possible, or do you recommend that?
So I would say it certainly is possible to do such a thing. You would effectively need to freeze the devices in time. So not the way most devices are implemented, not shut them off, but kind of stop their progression through time. So they stop timing the group, they stop doing everything, they show up someplace new, and they come back and start running in that sort of mode. One of the things that would make that challenging is that the devices are sending a sense when they're in survivability mode. They're sending a sense in the device time answer message. That's part of that timing control, a sense of real time. So they're sending the GPS epic time in that message. And that means that if the device somehow gets a sense of real time again, it'll fast forward the group into wherever time really becomes. It sounds like an existential problem, but there is some challenges associated with how you would actually get that to kind of move and migrate there. We use that global sense of time because it enables us to centrally coordinate these groups and get them all running in the same time and using the same transmission and reception opportunities.
Okay, thank you, Dave. So now question 19 from Daniel. As it seems, the group communication will be invisible to the gateways, since end devices send downlinks that the gateway cannot receive. So is this a problem? And if it's a problem, any solution? Thoughts to that?
Yes. So the general rule, without getting too complex in the formation of the groups, the general rule of thumb that we have used in our implementations has been that we generally consider that there is a device-to-device channel that the devices open up, and there's a unicast channel that they keep open to the network. So for example, if you have an alarm condition like this, you would send both on the unicast channel and on the device multicast channel the same message effectively back towards the network and towards the end devices. So that's how you would communicate in that model. Now that said, and certainly depending upon the gateways that you are using, whether they have filters on them or not, what regions you're operating on, you can also create these groups on frequencies that are not aligned with the standard downlink frequencies. That may or may not solve your problem, again, depending upon the actual gateways you have and the way that the LNS is configured to be able to support such a configuration. But it would be, in theory, possible to run the group on a frequency that the gateway can actually listen on. You do run into some issues there with the gateways potentially, again, transmitting and receiving on the same frequencies, which you would need to have a switch effectively on such a gateway.
Okay. Another question, which is number 25 from David. Can this device-to-device capability be used for OTA, so over-the-air activation, from one end device to another?
So today, that is, excuse me, that's not possible. So you wouldn't use this mechanism for that. Again, the device is centrally controlled, so it needs to be on the network, already operating before we can provision the multicast information, the keys, and the multicast address that's going to be used to coordinate the group itself. What you just described, though, is something that the relay technology can absolutely support.
Yes, so that's exactly what the relay can do. The relay is a battery-operated relay, and it's relaying normal traffic and also joint traffic. So indeed, you would use the relay for that. Then a question maybe more on the application. Question 17, would you support research into LoRaWAN connected devices monitoring explosive gases and smoke alarms for the residential sector?
I think that's a fantastic application of this technology. So it's really maybe the preeminent example of what we were looking to solve that has those requirements of survivability, of reachability, even in the event of all kinds of catastrophic situations. So I think it's a fantastic area of research.
So then maybe question number 30. Can we synchronize end node by the network server?
We synchronize end nodes by the network server. So I think that is in fact what we are doing. So the network server starts out as the primary source of synchronization, both in terms of the cryptographic material that's required to exchange messages securely, but also in terms of the timing information to establish those groups.
Okay. Then question number 26 on topology. With the multicast topology, can the end nodes, so I guess it's the device-to-device multicast topology, can the end nodes still transmit payload data across the network, arriving at the gateways for consumption and other?
Yeah, this is similar to the question we answered just a little while ago, where the traditional methodology that the gateways are implementing and the LNSs are implementing is they are not receiving messages on the downlink frequencies that are being used typically for these kinds of communications. You can steer the multicast group really to any frequency and any data rate that's available on the downlink configurations, but you would need to have an open demodulator on the gateway that was also listening in that area and not have any filters in place or other things in order for the gateway to receive that message. And generally speaking, your gateway wouldn't be transmitting to the group in that way. If you don't do that, the network can participate in the group with transmissions to the group from the network.
Okay. Then it's more a question. So question 27, I think, is a question on the experiments or POCs we've made. What is the maximum number of nodes you have used, and at what messaging rate per minute?
So again, keep in mind, so there's two things to consider here. So one of them is that we are still looking at battery operated devices. So in the normal state of the environment, these devices are not transmitting very often. In many cases, in some of these like the leak detector devices, they may only be normally transmitting like once per day or something like that, just a keep alive. When an alarm condition is heard, then the devices move to a very rapid transmission mechanism in order to get the alarm information conveyed. In the groups that we've been working with and establishing, I'd say we're probably typically less than a dozen, less than 12 or so nodes are typically making up that environment. But the messaging rates when the alarm conditions can occur can be quite rapid. I think in the order of probably every 15 seconds, 16 seconds, something along those lines. We are bound with the transmit opportunities that are defined in the Class B definition effectively. So we are looking at maximum transmit rate of about once per second is what you're able to do if you consume the entire space. Most of the groups aren't going to be set up with that frequency of transmission. The other thing that we do in the real world, and this is one of the areas that I think that multicast group methodology is very, very powerful. In the real world, we're worried about two different things. We're worried about there being congestion of the network because there are many groups. So think of an apartment building maybe, where you've got a methane leak detector and a gas main at each apartment, each of them forming their own little group. We don't want those groups to interfere with each other. So we need to shift them in frequency, we need to shift them in time, we need to shift them in data rate and transmit power in order to minimize the amount of collisions that we're going to see there. And then when we have an event like this, we need to make sure that there's no congestion collapse of the network, which means you can't have every device that detects the leak screaming all the time. So one of the goals that we have here is that there's still a paced mechanism. So when the alert is detected, the device begins to transmit relatively quickly in its available time slots, and then it backs that off. Any device that's part of the group that also hears that message can then know that an alarm is already being raised, and they don't necessarily need to raise that alarm themselves either. So that helps us bring the overall transmission rate of the group down while still conveying the important delivery of the information that is required to take the action to shut the valve off.
Okay, so we are close to the end of the Q&A session. So maybe one question, so question number 21, which is more of a business question on combining different applications in the same multicast group. For example, a fire sensor and a gas safety application, can they be part of the same multicast group? And would this help, by the way, Dave, with potential congestion?
So I think it definitely could help with that kind of congestion. And I would imagine this would be true when we say in the same application or a different application, certainly as described there, like a fire sensor, the gas sensor, maybe there's a water leak sensor or a safety, a security sensor on a door or a window. In a company that was combining all of those into a single pane of glass mobile application for the residents or the user, that would obviously make all the sense in the world to combine them into a single group. I think the scalability of that at large scale, so if you go back to the apartment building, you probably don't want the entire apartment building to be in one group. That's a lot of devices. We can support a lot of devices and protocol, but that's a lot of devices potentially contending for the same airspace. And something that we probably want to work towards fractionalizing that into smaller buckets of intentionally localized control.
Okay, so I think we can have one final question, which is 29. Is it correct that the relay specification doesn't yet support enabling grouping range extension? I have to say I don't completely understand what it means, but if it's maybe single hop, if it's related to single hop with the relay, when the relay is just expanding to one hop, so it's relay from the gateway to the relay, then to the end device, or the other way around, but no more than one relay in between. Or maybe there's a different meaning in the question that you get, Dave.
The only thing that I can think of that is still a limit within the relay is that the relay doesn't propagate a beacon. So forming a Class B group or a multicast group on the other side of a relay is still something that isn't yet defined. One of the things that you could do with what we've described here, though, is you can form that group as long as the group is always in survivability mode. So the group is always self-timing on the other side of the relay. That's something that could be created.
Okay, so thank you, Dave, for answering all these questions and giving and preparing this webinar. I think it's been really useful. We had a nice attendance today. Thanks to all attendants for listening and staying almost all of them to the end. So it was a great pleasure for us to welcome you today. And we are now going to end this webinar. You can watch it, the replay, and you can also download the slides of the webinar later. Thank you all. Bye-bye.
Thank you.